Hello everyone. In the previous lecture, we have discussed on work and energy. And in this lecture, we solve some numericals on work and energy. Let's see the first question. A block of weight W is given an initial velocity V0 along a horizontal plane and is brought to rest by friction in a distance x. Determine the coefficient of friction assuming that it is independent of velocity. So in this question, what is given? That is weight of the body W, the initial velocity V0, final velocity. It is considered in this question that the body comes to rest by friction. So the final velocity here we consider to be 0 and the distance traveled by the body is x. So this is given in the question. So here according to the question we draw this diagram. So here we consider the body of weight W. It is placed initially here and due to certain thing, this body W is moved from this particular place to this new place and the distance covered by the body is x, and this body comes to rest due to the frictional force which is given in the question. So if we draw the free body diagram of this body, so we have to consider the forces, the total forces acting on the body. So see, here we consider this is a body. It means as a body is there, it means its weight is there, that is W. And as this body is placed on a horizontal surface, so the reaction is exerted from this contact surface. So this is the reaction. And this body comes to rest condition due to the frictional force. It is mentioned in the question. So if this body is approaching towards this direction, so the frictional force must acting in the opposite direction. So this is the opposite direction. So here we consider the frictional force which is acting in opposite direction. And what we have to find here in this question, we have to find out the coefficient of friction, that is mu, right? So to solve this numerical, we have to use the equilibrium condition, and the equilibrium condition is, summation of Fy equal to 0. So first we consider this equilibrium condition. So see here, we consider only summation of F equal to 0. We are not considering summation of F minus ma equal to 0. See, what is the difference? Because along the y direction there is no displacement or there is no acceleration. So as acceleration is 0 along y direction or vertical direction, so minus ma term gets 0. So the equation reduced to summation of F y equal to 0. And along this y direction, what are the forces? That is Rn and W. So we can say that Rn minus W equal to 0 or Rn equal to W, right? Now we consider the work-energy theorem. According to the work-energy theorem, we know that the work done by the body is equal to change in kinetic energy. So work done is equal to change in kinetic energy. So work done means the force into displacement, right? The force into displacement. So see along which direction the displacement is there, that is along x direction, or you can say along the horizontal plane. So along horizontal plane, how many forces are there? That is only F. So this F is considered to calculate the work done, right? So force into displacement is work done. So here we consider the force into displacement. But see, here I have given one negative sign. Why this negative sign? Because this body is approaching in this way and the force is in the left side direction. The body is approaching towards right hand side, but this force is acting in the left hand side. So the directions for force and the displacement are in opposite. That's why it is considered here the minus sign. And change in kinetic energy, the final kinetic energy minus initial kinetic energy, final is half mvf square minus half nvi square. So here we consider vf as the final velocity and vi is the initial velocity. So vi is given in the question as v naught. It is given in the question as v naught, and vf, it is considered the finally the body approaches to rest condition. So vf is equal to 0. So as vf is approaches to 0, so this total term gets 0 and the equation becomes half m v naught 0. So vi is equal to v naught in the given question. So minus, this is minus, so minus minus cancels each other. Fx equal to half m v naught square. This m can be considered as w by g, and here F, this is frictional force, and frictional force is equal to mu into Rn into x, and Rn is equal to W, that already we proved it. So in place of Rn we substitute W, W cancels each other, and if we rearrange it we get mu is equal to V naught square by 2gx. So coming to the next question. A small block of weight W equal to 44.5 Newton is given an initial velocity V naught equal to 3 meter per second down the inclined plane as shown in figure. If the coefficient of friction between the plane and the block is mu equal to 0.3, find the velocity V of the block at B after it has travelled a distance of x equal to 15 meter. So it means here in the question it is asking that find out the final velocity. So according to the question, the weight of the body is 44.5 Newton. Initial velocity V naught, it is given 3 meter per second. Mu, it is given the coefficient of friction between the block and the inclined plane is 0.3. It is given here. And the distance travelled by the body from position A to position B, it is given as x equal to 15 meter. So here in this question we have to find out what is the velocity of the block at point B. It means the final velocity it is asking, that is Vf. And here in the question final velocity is considered to be V, so we consider here V. So Vf is represented as V and initial velocity is represented as V naught, that is 3 meter per second. So see here again we consider the equilibrium conditions. So let us consider this is the y direction and this is the x direction. So if this is the y direction, is there any displacement or is there any acceleration of the body? No, it is not accelerated along the y direction. So it means minus ma term gets 0 from the equilibrium equation, that is summation of f minus ma equal to 0. Minus ma is 0. So the equation reduced to summation of fy equal to 0. And as this is Rn and W cos 30 degree along this y direction, so Rn minus W cos 30 degree equal to 0 and Rn equal to W cos 30 degree. W is given as 44.5. By substituting this we get Rn is equal to 38.54 Newton. Now according to the work-energy theorem, we know that work done equal to change in kinetic energy. So work done, it means we have to consider the force into displacement. So the displacement is along x direction, so this we assume to be x direction. If this is x direction, so how many forces are there along this direction? So that is W sin 30 and F. So both these forces are along this x direction. So if this is along x direction, so due to this W sin 30 and F, the displacement made by the body is x. So we consider both these forces to calculate the work done. So how you have to consider this? So see, this body is moving or approaching in downward direction. It means we have to consider W sin 30 degree must be greater than F. So according to that, we consider here W sin 30 minus F whole bracket into x is equal to, this is change in kinetic energy, final kinetic energy minus initial kinetic energy. So Vf is given as V square and Vi is given as V naught. So now we substitute all the values here. M is considered to be W by G. Here also it is considered. And here we substitute the weight W value 44.5 sin 30 minus F. F is mu Rn. So here we consider mu Rn into 15 is equal to half W by G V square minus half W by G V naught square. This V we have to find out, and V naught is given as 3. The value of W we know, that is 44.5, and the value of G we know, that is 9.81. So it means if we substitute all the values and solve this value, we can get the value of V to be 8.927 meter per second. Thank you.